You're late, Zundamon. This is the cave of Sigma. There are lots of Sigma symbols gathered here.
Yeah, looks like it. So where's that Sigma we're looking for?
Actually, I haven't found it yet.
Wait a second. I've got a bad feeling about this. Whoa! This is?
It finally appeared. So the rumor that a Sigma mutated in this cave was true. Here, X is a real number. A real number is a number that can be represented by a point on the number line.
What? X is a real number? What in the world does that mean? Sigma notation was originally supposed to represent repeated addition. For example, here the terms from a sub 1 to a sub n are being added. Each term has the form a sub k, and k starts at 1 and increases by 1 until it reaches n.
That's right. In other words, n terms are being added here. Of course, this expression assumes that n is a natural number. But in the sum that just appeared, k runs from 1 to x.
So does that mean adding x terms? I don't really understand what that means. X is a real number, right? What in the world is a real valued number of terms?
It certainly isn't easy to understand. But sometimes we do want to consider such a thing. For example, let's consider the sum of the natural numbers from 1 to n. This is called a triangular number, and the nth triangular number is given by this formula. The important point is that the left-hand side assumes that n is a natural number, but the right-hand side can still be calculated even when n is not a natural number.
Now that you mention it, that's true.
Here, if we boldly substitute pi for n, even though n was originally supposed to be a natural number, we get this equation.
What? Are we really allowed to do that? What a strange equation.
We can even substitute a number smaller than 1 for n, at least formally. For example, if we substitute 1/2 for n and calculate, the result is 3/8.
This is strange too. But this is only for the case where the summand is k, right? What happens in a general case?
That seems to be exactly the problem this time. The result of a sum cannot always be extended in this way. We need to find a way to extend the natural number n to a real number x for a general sum of a sub k. But there's one thing I want you to keep in mind. This can be seen as an attempt to interpolate discrete values continuously. Interpolate discrete values continuously. There isn't just one way to do that. There are many ways to fill in the gaps. But among them, there may be a method that somehow feels natural. Let's try to find it. Now, I'd like to start exploring right away, but there's something we need to set up first.
What is it?
When extending the upper limit n to real values, just knowing the discrete values of the terms does not give us enough information. So let's assume that a real valued function f defined on the real numbers is given, and that each term has the form f of k. Since the function f is given, we can also use information between the terms. For example, f of 1.5.
I see. That certainly sounds useful. I think I understand the situation now. Okay, let's move on. Metan, look at this!
K runs from 1 to infinity. This is sigma notation for an infinite sum. Could this be our clue?
That seems very likely. Let's use it right away. Sigma notation for an infinite sum. Let's use it to add expressions of the form f of k. This sum continues forever.
F of 1, f of 2. Then f of n plus 1. And it keeps going forever. Let's set the convergence of this infinite sum aside for now, and proceed formally for a while. By the way, Zundamon, do you notice anything?
Huh? Even if you ask me? Come to think of it, f of n is right here. That means the sum from f of 1 to f of n is hidden near the beginning. We can express it like this using sigma notation.
Interesting. Let's apply this idea. By letting k run from 1 to n in sigma notation, we obtain the sum from f of 1 to f of n. This is a finite sum, but it can actually be expressed using infinite sums. First, we have f of 1. f of 2 and so on, forming an infinite sum that continues with f of n and beyond. If we subtract the infinite sum starting with f of n plus 1, we are left with the sum from f of 1 through f of n, which is exactly the original finite sum.
Oh, I see. If we express this again using sigma notation, each term in the first infinite sum has the form f of k. And each term in the second infinite sum has the form f of n plus k. If we combine them into one infinite sum, we get this.
Excellent, Zundamon. A finite sum of n terms can be expressed like this using an infinite sum. To represent the finite sum, we add infinitely many terms while subtracting the extra terms after the nth one.
The question mark here makes me uneasy, but let's ignore it for now. Still, this equation? It looks cool, but what is it useful for?
Look carefully, Zundamon. The natural number n on the left-hand side cannot be directly extended to a real number. But on the right-hand side, the upper limit n has been replaced by infinity, and instead, n appears here. Now we can naturally extend n to a real number. Since f is a function, the expression f of n plus k makes sense whether or not n is a natural number.
Huh?
So let's boldly replace the natural number n with the real number x. This is our definition of adding x terms.
What? Okay. The sum on the left-hand side looks unfamiliar, but the one on the right-hand side is just an infinite sum. So, if we set convergence aside, I think I understand what the expression means. So does this mean we've defined the summation on the left in terms of the one on the right? But it still feels strange. If we adopt this definition, it looks like some strange things will happen. Let's consider a sum of half a term. This is just the previous equation with x replaced by 1/2. Let's expand the infinite sum and write it without sigma notation. Then we get this.
I understand your point. A strange infinite sum has appeared. But can we really interpret this as adding half a term? By extending sigma notation, we may have stepped away from the intuitive idea of adding a natural number of terms, and caught a glimpse of a strange new world. But we cannot stop here. Let's move on.
Right. For now, we've extended sigma notation and defined a sum up to a real number, x. The question mark here bothers me, but let's ignore it for now. Huh? What's this?
It appeared already. We don't need to defeat any monsters, but we do need to solve math problems. Let's evaluate this expression right away.
Got it. It looks like we need to calculate a sum of powers of r. But x is not a natural number. It's a real number, so we need to use the definition from earlier. We defined a sum up to the real number x like this. It is defined as a kind of infinite sum. Now let's apply this definition. The sum of r to the power of k minus 1 up to x means this. Here, we replaced f of k in the definition with r to the power of k minus 1.
That certainly looks right.
Yes. Now let's factor out r to the power of k minus 1. Then we get something like this. Since 1 minus r to be x does not contain k, we can take it outside the summation. What do we do from here?
Look closely at this part, Zundamon. This has the form of a well-known infinite sum called a geometric series, so we can calculate it easily. Since the absolute value of r is less than 1, this infinite sum converges to 1 over 1 minus r.
Come to think of it, I may have seen that formula before. In that case, the answer is this.
Looks good. Now we've solved the problem. This equation has the same form as the geometric sum formula with first term 1. The difference is that x is a real number rather than a natural number.
I see. So this is an extension of the geometric sum formula. That means our extended definition of sigma notation is working properly.
So far, everything looks fine. But
what's wrong?
Zundamon, get down!
What? Whoa, What is this? Another problem appeared.
We were too late.
Still, this one looks easy. Let's just calculate it. This problem asks us to find the sum of x ones. The answer is, of course, x.
Wait, Zundamon. If x were a natural number, that calculation would certainly be correct. But here x is a real number, so we need to calculate it properly using our definition.
Oh, right. We defined a sum up to the real number x, like this. Then let's calculate it according to the definition. In this example, we just need to replace f of k with 1. Then we get this. This is really easy. Since 1 minus 1 is 0, we just add infinitely many zeros. Naturally, the result is also 0. So, in summary, the answer to this problem is 0. Alright, let's move on.
Wait a moment.
What is it this time?
Doesn't something look wrong with this equation?
Adding up ones gives us 0. How can that be?
Here we are considering a sum up to x. Since x is a real number, this is not a sum in the usual sense. Perhaps the simple intuition of adding up ones does not apply. No, even so, this equation is clearly false when x is a natural number. In other words, this sigma is not an extension of ordinary sigma notation.
Did we make a mistake?
Stay calm. We should first consider a finite cutoff.
Explain.
Very well, let me explain. I want you to recall this equation. This is the equation we used just before defining a sum up to x. We defined a sum up to x by replacing n with x. But perhaps this equation itself is wrong.
That may be true. We were pretty careless with infinite sums.
So before jumping straight to the infinite sum, let's first consider a finite sum cut off at m. Does this finite sum equation actually hold? If not, what exactly is missing? The clue should be hidden somewhere around there.
Understood.
I'll write the finite sum up to n here. Separately, I'll list the values of f of k in order. We begin with f of 1, f of 2, and so on. Then, f of n, f of n plus 1. And continue after that, through f of m, f of 1 plus m, and all the way to f of n plus m. Assume that m is sufficiently large. More specifically, as you can see from f of m being written to the right of f of n, we are assuming that m is greater than n.
I see. So far, so good.
Now let's see how these correspond to the finite sums. First, which part corresponds to f of k?
Since k runs from 1 to m, f of k runs from f of 1 to f of m.
Exactly. Then which part corresponds to f of n plus k?
Give me a second. When k is 1, f of n plus k corresponds to f of n plus 1. And since k runs up to m, f of n plus k runs up to f of n plus m.
That looks right. Now let's look at this equation again. The left-hand side represents the sum from f of 1 to f of n. But on the right-hand side, we subtract the red underlined part from the blue underlined part. So we have subtracted this part unnecessarily.
Oh, you're right.
Therefore, the correct equation is this. This adds back the missing terms.
Since k runs from 1 to n in this summation, yes, it really does represent the missing terms.
Now we have the correct equation. Well, we want to extend the natural number n to a real number x. However, the right-hand side contains a sum of n terms. This expression assumes that n is a natural number, so we cannot extend n to a real number as it stands. The first idea is to replace m with infinity again. More precisely, we take the limit as m approaches infinity. But this alone does not tell us how to handle the sum of n terms. So although this is a fairly strong condition, let's assume that this limit exists. This is the limit of f of t as t approaches infinity. For convenience, we'll write this limit simply as f of infinity.
Alright, permission granted.
Since we are now taking the limit as m approaches infinity, the sum of n terms on the right-hand side becomes a sum of n copies of f of infinity. Here, k runs from 1 to n, but the summand f of infinity is a constant that does not depend on k. So, this is simply f of infinity added n times. So we can write it as n f of infinity.
Yes, that's right.
Now, when we take the limit as m approaches infinity in the other sum, it becomes an infinite sum.
This is the infinite sum we saw earlier.
Let's interpret this equation intuitively once again. To represent a finite sum of n terms, we add infinitely many terms, while subtracting the extra terms after the nth one. However, this method subtracts more than necessary. This part adds them back afterward.
Right.
Now, looking at the right-hand side again, the upper limit n has been replaced by infinity, and instead n appears in two places. In both places, n can naturally be extended to a real number. In other words, this expression still has a meaning even when n is not a natural number. Okay, let's replace the natural number n with the real number x. Then we obtain this equation.
We finally did it! We define the sum up to the real number x.
Although this is only under the assumption that the limit f of infinity exists. Also note that when x takes a value other than a natural number, the convergence of this infinite sum is not necessarily guaranteed.
Got it. We revised our definition of a sum up to x like this. Here, the term xf of infinity restores the missing part.
With this definition, perhaps we can calculate the expression that failed earlier.
Let's try it. Earlier, we tried to calculate the sum of the ones. If we apply the revised definition, we just replace f of k with 1. So we get this. Naturally, the limit is also 1. Since 1 minus 1 is 0, the infinite sum vanishes. Then only x remains. So, the sum of the ones becomes this.
This agrees with the intuition that adding up x ones gives x. It looks good. Since x can take real values, let's try substituting a specific value. For example, if we substitute pi for x, we obtain this equation.
What a strange equation.
As a special case, when the limit of f at infinity is 0, the correction term in this definition becomes 0. So this definition reduces to the original one.
Oh, that's right.
For example, in the geometric sum, the powers of r converge to 0 because the absolute value of r is less than 1. Therefore, the correction term was unnecessary, which is why the original definition worked without any problem.
So that's what happened.
I also have some unfortunate news.
What's this all of a sudden? This is the example from the beginning, right? If we replace n with x, it looks like we could get an equation like this.
Actually, even the revised definition cannot handle this example.
What? Even though it's such a simple example? Wait a second. In this example, the kth term is k. So I guess this corresponds to f of t equals t. As t approaches infinity, this clearly diverges to infinity.
That's right. Since the limit f of infinity diverges, this example cannot be calculated with our definition. To solve this, we could refine the definition further, or use a completely different approach. Instead of explicitly defining what sigma notation is, this approach specifies the properties it should satisfy as axioms. With this approach, we can define extended sums of polynomials from an early stage of the discussion.
I don't really understand it, but such an approach exists.
The theory of extending a sum to a non-integer number of terms is called fractional sums. For further extensions and other approaches, please see the links in the description.
That'll be helpful. Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.